right, so energy of phase changes. We talked about specific heat and the energy for that. There is actually equations for this, which I don't know why they said no equations here, but there are. So you're going to be doing Q equals, and we're going to have the heat of fusion times the mass. And I'm going to go into what heat of fusion is here in just a second. And then the other equation that we're going to use is the heat of vaporization times mass. So heat of fusion is the heat required. That's ugly. Let's try that again, you guys. Nope, it won't let me do it. Won't let me back off there. Let's try that H again. I'm trying to make that look a little bit better. So this equals the heat required that's supposed to be required to melt a sample. Okay, so what do you think this is? Yep, this is the heat required to vaporize a sample. Okay, and then you're going to multiply that by the mass. Can you email me their names? Okay, thank you. All right. So, like I said, we're going to calculate the heat released or absorbed when a phase change takes place. Yesterday's, or the equation that we've been using for specific heat, had a delta T component in it. And remember, during a phase change, the temperature doesn't change. So your delta T would be 0, and then your answer would be 0, because anything multiplied by 0 is 0. So that's why we're not going to have the delta T component. But it's essentially the same idea, except instead of using specific heat, we're using heat of fusion or heat of vaporization. Okay? And then you're going to multiply in mass. So if it's an endothermic, that we're absorbing heat from the atmosphere, the surroundings, and we're going to go from a solid to a liquid to a gas, or you could go directly from a solid to a gas. And then you know what the phase changes are for going the other direction. They talk about, this is called heat of fusion, because you're bringing together those molecules and you're essentially kind of like fusing them together, right? Fusing means to, like, if you've ever heard of like people having a bone break, they have to like fuse the bone back together with the bone fuses back together. Yeah, I'm just rambling now, aren't I? Sorry. Okay, so that's where they get the heat of fusion, and then the other one is the heat of vaporization. If this value is negative, then it's going to be going this direction. Okay, because it's going to be giving off that heat. And if it's positive, it's going to be going this direction because it's bringing that heat in to break those intermolecular forces. All right, so here we have a heating curve for mercury. We are going to calculate the heat to freeze 100 grams of mercury. So we've got 100 grams. We're going to multiply that by the heat of fusion here, which they gave us in kilojoules per mole. So that's a problem. Okay, so we've got to take 100 grams of mercury, and we need to change that into moles because this is given as kilojoules per mole. So I've got to get grams into moles. Okay. And I know for every 1 mole, I have 200.6 grams of mercury. And now I am going to use this value, and I'm going to do kilojoules per mole. So that's going to get rid of my moles. So I'm using these units, and now the kilojoules and the number go together. And that's in every 1 mole. And that'll get me my answer. Okay. So I've got 100, 200.6, 2.3. So I ended up with 1.15. Oh, no, I should do 4 sig figs, shouldn't I? We're talking about sig figs. You guys have those on your exam. So that would be 4.7. I needed 4 sig figs because this was my measured amount. And that would be kilojoules of energy. I'm going to change this next question so you're ready for one of these on your quiz tomorrow, because you're going to have one of these like this. Solid. Okay, so we are going to freeze this aluminum. Yep.
So, do you just do the one that it gives you in the problem, not the one on the table for sig figs?
Right. Yep. These are standard amounts. They're kind of like the values on your periodic table. So these won't count in. They're not going to factor into sig figs. These would be considered constants, kind of like when you were doing your speed of light. That was 3.00. That is a constant. Like, it's not a measured amount. It's an accepted value. Remember, the sig figs go back to your measurement tool. So what was being measured in this problem were the grams of mercury. These other things we got off of tables where nerdy scientists have spent years calculating them, and everybody's shook hands and said, yep, we agree on these. They're constants. So you're not measuring these. The only time you're applying sig figs is when you've got a measured amount. So really, this guy, I should have had 100.0 down here in my problem if I really wanted to do this right. And then that would have alerted me to the fact that I needed 4 sig figs in my answer. Okay. All right. So we are going to take this aluminum. We are going to freeze it at 933 Kelvin. And then we are going to cool it. What do we want to cool it down to? Room temperature? Want to do room temperature? So 298 Kelvin. Okay. So we're going to start it out here, and then we're going to cool it. And actually, we should start. I wonder what it's vapor. In Celsius. Okay, okay. So let's start this out. I want to start this out, and I'm going to start it out at 2,500 degree, or 25 Kelvin, 2,500, yeah, Kelvin. Okay. Then we are going to freeze it at this temperature. Okay. And it is going to condense at 2467. So we're going to start it out at this temp. It's going to condense at this temperature. And then we're going to freeze it and cool it further all the way down to room temp. Okay? Don't get scared. It's fine. All right. So step one with this is I'm going to snip this and bring it into a Word doc so I have more room to work with. Okay, there we go. Now we are going to paste it into here, and now I got room to work. Okay, so we are going to start out, and the first step that we need to do is find the specific heat for, so I got to give you one more value. Okay, so we need the specific heat of aluminum vapor, and that is 0.9 joules per grams degrees Celsius. Right? I also need the specific heat for aluminum liquid. And that's going to be, so this is for vapor, this is for liquid. That is going to be 1.33 joules per grams degrees Celsius. And the last one I need, the specific heat of aluminum solid, which they may have given us in, they did not give us in the problem. Huh. That's interesting. It's the same as that one. Okay. That's not right. Let's just make up a number. It may not be exactly right, but we're just going to go with it. See, usually I'm a little more polished for you guys because you get me. After I've been through this once, but I didn't go through this with second hour today because we had those demos. So 113, divide by 1,000 and multiply by 27. Okay, so I think this is around 3.1 is if I did my calculations right. Okay, and we're going to go with it anyway. I'll show you how to do the problem with it at least. Okay, so step one, you need to go from the gas to the vaporization temp. So when it's going to condense, or condensation point. I guess it would be condensation. So we are cooling it from 2,500. Oh, that's Kelvin though. It'll still work because it's the same difference in temp. Okay, yeah, that'll still work. So we're going to take this and we're going to cool it down to Kelvin here. We're going to cool it down to the point where it's going to condense. So that's going to be 2467. So you're going to take, and we're going to figure out Q for this. So that would be your MCAT formula. So we had 2.5 moles of aluminum. We got to figure out what that is in grams. So we're going to multiply that by 27 to get that into grams. 2.5 times 27 gives me 67.5 grams. All right, so my mass is 67.5. My specific heat for this, we're going to say is 3.1. I'm hoping that's what it is. It's going to be close. And then I need to do a delta T. So how much did this lose to get down to here? Well, 2,500 minus 2467. I'm at 33 degrees Celsius for a difference. Okay. All right. I know these are in Kelvin and I said Celsius. But remember, if we just add 273 to this and 273 to this and then subtract, you're still going to end up with the same amount. Does that make sense? Okay. So I'm going to multiply these out together, and this is going to be my first value. So 33 times 3.1 times 67.5. So that is a Q value in joules of 6905, and that's going to be joules. So that's our first amount. So we want to keep track of this guy here, and then we've got to figure out another amount. Okay. So that's step one. Step two then. We are then going to take this material that is now, it's going to go through a condensation amount. So our Q here is going to equal our heat of fusion, which is 10.9. And we're going to multiply it by, they gave us moles, so we're just going to keep that in moles. And that's going to give us a kilojoule amount. Now, this was in joules. We want it in kilojoules, so I'm just going to do it there. I just moved the decimal over. All right, so I'm going to multiply this 10.9 times 2.5, and that's going to give me 27.25 kilojoules. So that's my second amount. That's to get me to the liquid state. Step three, we've got to take that liquid and we need to cool it down to where it is going to freeze. So it's going to freeze at 933. So we're going to go from 2467 minus 933. So my delta T there is going to be 1534. So my mass is, and I'm just essentially repeating this, except I'm changing this number to this guy. And I'm changing the amount of temperature change. So my mass is going to be the same, 67.5. I'm going to multiply by the specific heat for this liquid, which is 1.33. Then I'm going to go through my temperature change. So now my temp in this one is going from 2467 down to 933. 933. So I'm cooling this down until it gets to the phase change where it's changing into a solid. And the temperature difference there is 1534. So I'm going to multiply these together. So it's 67.5, 1534, and 1.33. And then I'm going to divide by 1,000 to get it into kilojoules. So that's going to give me 137.71. And that's going to be kilojoules. I divided by 1,000 to get it into kilojoules. That is going to be my third amount. Then I need to go through the phase change where it is going to go from a liquid to a solid. So I'm going to take, and I'm going to do my Q value. I'm going to take my moles of substance, and I'm going to multiply it by my, oh shoot, did I use the wrong value in this one? I used 10, dadgummit, you guys. I should have used 284 here. Shoot. This should have been 284. Well, this would have been our amount to go from this to the liquid to the solid. So I just got these out of sequence. So this would have been step 4. The math's still the same. So then if we back this up and do this as a step 2, this would have been our gas to a liquid. Maybe you could do an error there. That's 284. So my Q value here is going to be 710. And that's going to be kilojoules. And then the last step I need to take is to cool this down to the point where I am at 298 Kelvin. So I'm going to go through this. This is going to be step 5. So step 5, we are going from 933 Kelvin down to 298 Kelvin. So that's my temperature change there, 933 minus 298. And that's going to be a delta T of 635. All right, so we need to go back up here and grab, we had 67.5 grams. We're going to multiply that by the specific heat, which was the 0.9 joules per grams degrees Celsius. And we're going to multiply that by 635 Celsius for our temperature change. All right, so that's going to give me, that's not right. That can't be right. That's why. That's why. 635 times 67.5 times 0.9. All right, there we go. And then I'm going to divide this by 1,000 to get it into kilojoules. And my kilojoules are going to equal 38.6 kilojoules. All right, the last step then is to add all of these values up together. So we're going to add this guy and this guy together. 710 plus this guy, which is 137.7 plus 27.25 plus 6.905. All right, so total amount here. Our grand total is 920 kilojoules of energy released. Energy is being released. Do you need me to go through another one of those? Yeah. Okay. We are going to do, I don't know, you can find some spare paper somewhere out there. I don't know where. We're going to go through this with water, okay? Because water I can find values from, okay? We are going to start out with steam that is, I don't know, Celsius. What do you want to make it? 314 degrees Celsius. Let's do that. Okay. And we want to know how much energy is released when that steam is cooled to, let's do a negative. Sometimes it gets this cold in Wisconsin. Maybe, I don't know. It gets cold. We're going to do negative 25 Celsius. Okay. So our plan, step 1, we have to take this guy right here. We have to cool him down to the point where he's going to condense into a liquid. So I'm going to go from 314 degrees Celsius down to what temp? 100. Yep. So I have to do the math on that. Oh, I need a mass of this. How many grams do we want? 100 grams? Okay. So 100 grams of steam. Okay. So I need to cool that down to 100 degrees Celsius. So we're going to do a math problem here with that. Then I have to go from 100 degrees Celsius steam to 100 degrees Celsius liquid, right? So I'm going through that phase change. And all I'm doing is going from a gas to a liquid. Then I have to take that 100 degree liquid and I have to cool it down to what? 32 Fahrenheit, but we're in Celsius, 0 degrees Celsius. Okay. Then I have to go from 0 degrees Celsius liquid to what? To what? Solid. Yep. And you could think of that as ice, whatever, however you want to think of it. And then we have to cool that 0 degrees Celsius solid down to negative 25 degrees Celsius. Okay, so we're going to have 4 separate problems here that we're doing. So step 1, we are going to use our Q equals, and I've got to look up the specific heat for steam for water. Water vapor. All right, so that is 1.9. So specific heat of water vapor, C for water vapor. And that is, let's just, no, that's not right. There it is, 1.9. Okay, so I'm going to take my mass of my steam, and you guys wanted it to be 100 grams. I'm going to multiply that by my specific heat here. And then I'm going to multiply that by the change in temperature. So I'm going from 314 down to 100. So that's going to be a difference in 214 degrees. And I'm going to come up with a value for that. So 100 times 1.9 times 214. And that ends up being 40660, and that would be joules. If you want to do it in kilojoules, you just move your decimal point over 3 spots. Okay. Then I need to go and I need to do that heat of fusion equation or heat of vaporization equation. I need the mass again, and I need the heat of vaporization for water. Okay. And that I'm looking up and it says 2260 joules per gram. So I end up with 226000 joules here. Next up, I need to take this and I need to convert this down. So this is 100 grams. Specific heat of water, you guys have been working on that lately, so you know that. And this is cooling 100 degrees. So I end up with 41800, and that's going to be joules. Then I need to go through the heat of fusion. And that is 3355. 333.55. I'm going to multiply that by my 100 grams. And my Q value here is 33355 joules. And then the last part, we are going to find the specific heat of ice. Okay, that's 2.03. So Q equals 100 grams times 2.03 joules per grams degrees Celsius times, and how much should it change in temperature? 25. All right, so 25 times 100 times 2.03, and I ended up with 5,075 joules. The last thing is we've got to add up all of these numbers. Now, if you have one of these fancy calculators, you can go up and grab your figures, and it makes it a little bit faster than typing all of those in. If you don't know how to do that, come and see me. It'll only take me 2 seconds to show you how to do it. It makes life a lot easier. All right. So my grand total that I got with all of that was 346,890 joules. If you wanted to do that as kilojoules, it would be 340, let's just round it off, 347 kilojoules. Finished just in time.